The year is 363 AD. Persian defenders peer over the walls of their fortress, confident in their massive stone barriers. They've withstood Roman sieges before, but today, few knew that Rome's engineers had brought something different, something they'd never seen coming. A quiet monster that could hurl death from distances they thought impossible. While the Persians prepared for ladders and rams, they never saw Rome's deadliest artillery machine coming. The Onager. You're watching Great History, your daily history channel. I dig deep so you don't have to. We're on the road to 500,000 subscribers. So if you're loving these deep dives into ancient warfare, hit that subscribe button and let's uncover history's most devastating siege weapon together. This is the story of how Rome solved the deadliest problem in ancient warfare. How do you break walls that seem unbreakable? By the 4th century AD, fortress walls had evolved into engineering marvels. We're talking about barriers 40 feet high and 15 feet thick. Solid stone and mortar that could laugh at arrows and shrug off battering rams. The walls of Constantinople stretched for miles, punctuated by towers that rose like stone giants above the landscape. Traditional siege warfare was a nightmare of blood and time. Roman legions would spend months, sometimes years, camped outside enemy cities. Soldiers died of disease faster than they fell to enemy arrows. Resources drained away like water through sand. Careers ended in the mud of prolonged sieges. The Romans tried everything. Massive siege towers that took weeks to build, only to be burned by flaming arrows. Battering rams that required hundreds of men to operate, making them sitting targets for defenders. Undermining tunnels that often collapsed, burying engineers alive in the darkness below enemy walls. But here's what history books often miss. It wasn't just about breaking stone. Sieges were psychological warfare. Defenders needed to believe their walls were impregnable. The moment doubt crept in, the instant they realized their barriers could be breached, morale crumbled faster than mortar. Roman commanders knew this. They needed something that could reach farther than arrows, hit harder than rams, and strike terror into hearts that had never known fear. They needed to turn siege warfare from a war of attrition into a demonstration of overwhelming force. The answer lay in principles of physics that would later power medieval trebuchets and modern artillery. But first, Roman engineers had to solve a problem that had plagued military technology for centuries. How do you store enough energy in a mechanical device to hurl massive projectiles across impossible distances? Traditional catapults used twisted rope or sinew torsion engines that could launch arrows and small stones, but they lacked the raw power needed to crack fortress walls. What Rome needed was something different, something that combined the stored energy of a crossbow with the massive throwing arm of a catapult. They called it the Onager, named after the wild ass that kicked with deadly force. And like its namesake, this machine would deliver a kick that could shatter more than just. Few knew the real terror came from a deceptively simple principle: torsion amplification through mechanical advantage. The Onager wasn't just another siege engine. It was a revolution in applied physics that would change warfare forever. Picture this: a massive wooden frame, 15 feet long and 10 feet high, built from seasoned oak timbers thick as a man's torso. At its heart lay the secret: a horizontal beam suspended in a frame of twisted sinew ropes, each rope containing hundreds of individual strands wound tight as piano wire. Here's where Roman engineering genius shows itself. The throwing arm, a 12-foot lever carved from the hardest wood available, was inserted through the middle of these twisted rope bundles. When cranked back, the arm stored tremendous torsional energy, like a massive spring compressed to its breaking point. But the Onager was more than just a big crossbow. Roman engineers had discovered something that wouldn't be fully understood until centuries later: the principle of angular momentum conversion. The throwing arm didn't just flip forward, it accelerated through its arc, converting rotational energy into linear force with devastating efficiency. The projectiles were works of art themselves. Stone balls weighing 60 to 100 pounds. Carved smooth as billiard balls and weighted for perfect balance. Some were filled with pitch and set ablaze. Ancient incendiary rounds that could start fires behind enemy walls. Others contained caltrops or sharp metal fragments, turning the Onager into an ancient fragmentation weapon. Loading required a crew of 8 men working in perfect coordination. The arm was cranked back using a windlass system, a horizontal wheel with handles that allowed soldiers to multiply their force. It took nearly 300 turns to fully cock the machine, building tension that could literally tear lesser materials apart. The release mechanism was ingenious in its simplicity. A bronze trigger held the arm in place, bearing tremendous stress. When released, the arm snapped forward with the force of a thunderbolt, striking a padded crossbeam that absorbed the shock and transferred every ounce of energy into the projectile. You can see why Roman engineers were so proud of this machine. It combined metallurgy, woodworking, and physics in ways that wouldn't be matched for centuries. The bronze fittings were cast to tolerances that required master craftsmen. The wooden frame used complex joinery that distributed stress across multiple load-bearing points. Notice how every component served multiple purposes. The heavy base provided stability and absorbed recoil. The adjustable angle mechanism allowed precise targeting. Even the rope torsion bundles could be adjusted, tightened for maximum power or loosened for maintenance. But here's what made the Onager truly revolutionary. It was the first siege engine that combined massive projectile weight with impressive range. While earlier catapults could throw light objects far or heavy objects short distances, the Onager could hurl a 100-pound stone ball over 400 yards with accuracy that would make a modern artillery officer jealous. This wasn't just mechanical engineering. It was applied psychology. The Onager was designed to be as terrifying to watch as it was devastating to experience. The numbers tell the story of Roman engineering ambition. A fully assembled Onager stood 15 feet high, weighed over 4 tons, and generated muzzle energy equivalent to a modern 100. But those raw statistics don't capture the precision engineering that made it possible. Let's break down the physics. The torsion system worked on principles that wouldn't be fully understood until the Renaissance. Each rope bundle contained roughly 400 individual strands of twisted sinew, typically from oxen or horses. When properly tensioned, these bundles could store kinetic energy equivalent to a coiled spring weighing several tons. The throwing arm lever multiplied this force through mechanical advantage. At 12 feet long, with the pivot point placed 2 feet from the rope bundle, the arm created a 6-1 leverage ratio. This meant every pound of torsional force became 6 pounds of throwing power at the projectile release point. Modern reconstruction experiments have revealed staggering performance figures. A properly built Onager could accelerate a 100-pound stone to over 100. The projectile maintained lethal velocity for over 300 yards, carrying enough kinetic energy to punch through 3 feet of solid masonry. The engineering tolerances were remarkable for ancient technology. The rope torsion bundles had to be tensioned within 5% of optimal or the machine would either underperform or tear itself apart. The bronze pivot bearings were machined to fit tolerances measured in fractions of inch. Even the projectiles were carved to specific weight distributions, heavier at the base for stable flight. Roman military engineers developed standardized component systems that allowed onagers to be partially disassembled for transport. The main frame broke down into 12 major pieces, each designed to fit on a standard military wagon. A trained crew could disassemble an onager in 4 hours and rebuild it in 6, crucial for armies that needed to move quickly between siege targets. The aiming system showed sophisticated understanding of ballistic principles. Elevation was controlled by an adjustable bronze bracket that could be set to precise angles. Lateral targeting used a rotating base platform with bronze bearings. Roman artillery manuals preserved in fragments described firing tables that calculated range based on elevation, angle, and rope tension. Loading procedures required choreographed precision. The windlass cranking system used a 4:1 gear ratio, meaning it took 1,200 total turns to fully cock the machine. 8 men working in pairs could complete this in roughly 10 minutes. Remarkably fast for such a powerful weapon. But here's where Roman engineering genius really shows. The stress distribution system. Every component was designed to handle forces far exceeding normal operation. The oak frame timbers were joined using complex mortise and tenon joints reinforced with bronze braces. The rope anchor points were backed by bronze plates that distributed stress across the entire frame structure. The recoil absorption system was equally sophisticated. When the throwing arm struck the padded crossbeam, the entire machine absorbed tremendous backward force. Roman engineers solved this by designing the base frame to flex slightly, absorbing recoil energy that would otherwise shake the machine apart or throw off its aim. Quality control was obsessive by ancient standard. Military engineering manuals specified wood seasoning requirements, metal alloy compositions, and rope tensioning procedures. Every onager built to military specifications underwent performance testing that measured range, accuracy, and structural integrity. You're looking at a machine that represented the absolute pinnacle of pre-gunpowder artillery technology. Roman engineers had pushed mechanical engineering to theoretical limits that wouldn't be exceeded until the invention of steel and precision machine. It wasn't just the physics that made the onager devastating. It was the psychology. Imagine standing on fortress walls, watching Roman engineers assemble this wooden monster 400 yards away. You've never seen anything like it. The throwing arm rises like a giant's club. Soldiers work around it like ants, serving some mechanical god. Then comes the moment of truth. The arm snaps forward with a crack like thunder. A massive stone ball arcs through the sky, growing larger as it approaches. You have perhaps 3 seconds to comprehend what's happening. Then 100 pounds of carved stone explodes against the wall 20 feet below your position. The sound was as important as the impact. Roman accounts describe the voice of the onager, a sharp crack followed by a whistling roar as the projectile cut through air. Defenders could hear death coming, but were powerless to stop it. But the onager was more than just a weapon. It was psychological warfare engineered to maximum effect. Roman commanders positioned these machines where defenders could see them clearly. The loading process became theater, a slow, deliberate demonstration of Roman engineering superiority. Watch how Romans deployed them strategically. Multiple onagers working in sequence created a drumbeat of destruction that never let defenders rest. One machine would fire while others reloaded, maintaining constant pressure that ground down enemy morale hour by hour. The projectiles themselves were chosen for psychological impact. Flaming balls that traced fiery arcs across the sky, stone spheres that struck with thunderous crashes. Some were even loaded with severed heads or rotting animal carcasses. Ancient biological warfare designed to spread disease and terror. Roman military psychology manuals, yes, they had those, recommended specific targeting sequences. First shots aimed at walls to demonstrate range and accuracy. Second volleys targeted towers where enemy commanders stood. Only then would they systematically begin reducing fortifications stone by stone. The mere presence of onagers often ended sieges before they began. Cities that might have resisted for months surrendered within days of seeing Roman artillery crews assembling their machine. Word spread along trade routes about the thunder weapons that could knock down any wall. Here's what modern military psychologists recognize. The onager created learned helplessness. Defenders realized their walls, their ultimate protection, could be systematically destroyed by an enemy standing safely beyond arrow range. The psychological foundation of fortress defense crumbled along with the stone. Roman commanders understood this better than their enemies realized. Siege warfare wasn't just about taking cities, it was about demonstrating Roman technological superiority to anyone who might consider resistance. The onager became a symbol of Roman power as much as a military weapon. The siege of Amida in 359 AD shows the onager at its most devastating. Persian forces had surrounded this crucial Roman fortress city in modern-day Turkey. The walls were massive, 40 feet high and reinforced with towers that had withstood decades of assault. Ammianus Marcellinus, who witnessed the siege personally, describes the moment Roman relief forces arrived with their artillery train. The machines were assembled with such skill that even veteran soldiers stopped to marvel at their construction. The Romans positioned 12 onagers at carefully calculated distances, not close enough for Persian arrows to reach the crews, but near enough for devastating accuracy. The bombardment began at dawn and continued for 18 hours straight. Here's what made this siege legendary. The Romans didn't just attack the walls, they systematically targeted the psychological foundations of defense. First volleys struck the main gates, demonstrating that no part of the city was safe. Second waves targeted the towers where Persian commanders coordinated defense. The stone projectiles did more than physical damage. Each impact sent shock waves through the entire wall structure. Mortar joints loosened, stone blocks shifted. After 6 hours of bombardment, sections of wall that looked intact were actually held together by little more than gravity and hope. But the real breakthrough came when Roman engineers began using specialized ammunition. Archaeological evidence from Amida shows fragments of hollow stone balls filled with incendiary materials. These ancient artillery shells exploded on impact, spreading fire that defenders couldn't reach to extinguish. The psychological impact was immediate and devastating. Persian soldiers who had never feared arrows or swords found themselves helpless against weapons that struck from beyond their ability to retaliate. Desertion rates spiked. Morale collapsed faster than the walls themselves. Roman battlefield reports preserved in military archives reveal sophisticated artillery tactics. Onager crews used ranging shots to establish distance, then switched to concentrated bombardment of specific targets. They coordinated with infantry assaults, timing wall breaches to coincide with ladder attacks. The siege of Bezabded demonstrates another tactical innovation. Roman forces used onagers to create suppression zones, areas where concentrated artillery fire prevented enemy reinforcements from reaching threatened wall sections. This allowed Roman engineers to work on undermining operations without interference. Notice how Romans adapted the onager for different tactical situations. At Pirasabora, they mounted machines on naval vessels for riverine assault operations. The ships provided stable firing platforms that could move to optimal ranges while staying beyond enemy archery. Field modifications were common and sophisticated. Onager crews developed rapid-fire techniques using pre-positioned ammunition. They created mobile versions with lighter frames for cavalry support operations. Some were even modified to launch multiple smaller projectiles instead of single large stones. The Battle of Strasbourg in 307 AD shows onagers in open field combat. Roman forces used them as long-range artillery against Germanic tribal formations. The machines couldn't match their siege performance, but the psychological effect on barbarian warriors who had never seen mechanical weapons was overwhelming. Roman tactical manuals describe coordinated artillery barrages involving dozens of machines. The sound alone, multiple onagers firing in sequence, created noise levels comparable to modern artillery bombardments. Enemy formations often broke before projectiles even landed. But here's what made Roman artillery doctrine revolutionary. They understood combined arms tactics centuries before the term was invented. Onagers supported infantry assaults, provided covering fire for engineering operations, and created gaps that cavalry could exploit. The numbers tell the story of battlefield effectiveness. Siege durations decreased by an average of 60% when Roman forces deployed onager battery. Casualty rates for Roman assault troops dropped dramatically because artillery preparation eliminated most defensive positions before infantry attacks began. Roman military engineering was never static. Each campaign brought modifications, improvements, and innovations that pushed onager technology toward theoretical perfection. The earliest models from the 3rd century were crude by later standards. Heavy, slow to assemble, and prone to mechanical failure. But Roman engineers learned from every broken rope, every cracked timber, every missed shot. What emerged was a systematic approach to weapons development that wouldn't be matched until the modern era. By 350 AD, standardized onager designs had evolved into precision instruments. The Type 7 model, designated in Roman military nomenclature, could be assembled by trained crews in under 4 hours using standardized components. Each piece was numbered and fitted with bronze markers indicating proper assembly sequence. Material science advanced in parallel with mechanical design. Early onagers used whatever rope was available, hemp, flax, even horsehair in desperate situations. Later models specified sinew from specific animal types, aged and processed according to precise military standards. The difference in performance was dramatic. Roman metallurgy pushed bronze working to new limits. The pivot bearings that supported the throwing arm required alloy compositions that combined strength with wear resistance. Archaeological analysis of onager components shows bronze formulations that weren't matched in Europe until the 18th century. But the real innovation was modularity. Later Onager designs broke down into completely interchangeable components. A damaged throwing arm from one machine could be swapped onto another without modification. Rope bundles were pre-tensioned at workshops and transported ready for installation. Field maintenance became a sophisticated discipline. Roman artillery units included specialized technicians, ballistari, who understood the complex engineering principles underlying onager operation. These men could diagnose mechanical problems, adjust tension settings, and modify machines for specific tactical situations. The siege of Ctesiphon in 363 AD showcased the ultimate evolution of Roman artillery doctrine. Emperor Julian's forces deployed over 60 onagers in coordinated battery formations. Each battery could deliver concentrated firepower equivalent to a modern artillery regiment. Quality control reached obsessive levels. Military engineering manuals specified wood grain patterns, metal hardness standards, and rope tension measurements, accurate to fractions of a pound. Every onager built to military specifications underwent performance testing that measured range accuracy to within 10 yards at maximum distance. Roman engineers developed specialized variants for different tactical roles. Siege models maximized projectile weight and impact force. Field artillery versions emphasized mobility and rapid deployment. Naval adaptations featured bronze corrosion-resistant components and shock-absorbing mounting systems. The most advanced models incorporated feedback systems that modern engineers would recognize. Adjustable rope tensioning allowed crews to modify power output for different ranges. Elevation mechanisms could be set to precise angles using bronze protractors marked in degree. By the late 4th century, onager technology had reached a plateau that represented the absolute limits of pre-gunpowder artillery. The machines were as powerful, accurate, and reliable as physics and materials science would allow. What separated Roman artillery from earlier siege engines wasn't just superior engineering, it was integration into comprehensive military doctrine that treated siege warfare as a systematic science. Roman military manuals described artillery deployment with mathematical precision. Onager positioning followed geometric principles that maximized field of fire while protecting crews from counter-battery fire. Battery formations used overlapping coverage zones that eliminated dead space where defenders might find safety. The logistics were staggering by ancient standards. A single onager required approximately 2 tons of specialized ammunition for extended siege operations. Roman quartermaster services developed supply chains that could deliver carved stone projectiles, rope maintenance materials, and replacement components to armies operating hundreds of miles from manufacturing centers. Training programs created professional artillery specialists who understood engineering principles as well as tactical application. These weren't common soldiers assigned to siege engines. They were technical experts whose skills were as valuable as those of military engineers or medical specialists. Roman artillery doctrine emphasized systematic destruction over random bombardment. Target selection followed priorities designed to maximize psychological as well as physical impact. Command structures were always primary targets, followed by defensive positions. Then civilian morale targets like temples or marked. Field manuals described ammunition selection with scientific precision. Different projectile types for different tactical situations. Solid stone for wall breaching, incendiary rounds for burning wooden structures, fragmentation loads for anti-personnel effect. Roman artillery crews carried standardized loads that gave them flexible response capability. The integration with other military branches was seamless. Onager crews coordinated with engineers who prepared firing positions, cavalry units that protected artillery from counterattacks, and infantry formations that exploited gaps created by bombardment. But here's what made Roman artillery doctrine revolutionary. They understood suppression as well as destruction. Concentrated onager fire could prevent enemy units from maneuvering, even when it didn't cause significant casualty. This allowed Roman commanders to control battlefield tempo and dictate engagement terms. Communication systems linked artillery batteries with observation posts and command units. Flag signals, Trumpet calls and messenger networks allowed real-time fire control that concentrated multiple machines on priority targets within minutes. Roman military engineering established artillery parks, fortified positions where onagers could operate under protection while maintaining clear fields of fire. These installations included ammunition storage, crew quarters, and workshops for equipment maintenance. The psychological integration was equally sophisticated. Roman commanders used artillery as diplomatic tools, demonstrating firepower to potential enemies before negotiations began. The mere presence of onager trains often convinced hostile cities to surrender rather than face siege. While most people think of onagers as siege weapons, Roman tactical innovation found applications that revolutionized multiple aspects of warfare. The Battle of Mursa in 35-1 AD demonstrates onager effectiveness in field combat. Roman forces used artillery to break up barbarian cavalry charges before they could reach infantry lines. The psychological effect on horses, animals that had never experienced mechanical projectiles, was devastating. Roman engineers developed mobile artillery tactics that anticipated modern self-propelled guns by over a millennium. Onagers mounted on reinforced wagons could move with advancing armies, providing fire support for infantry operations and cavalry action. Naval applications pushed engineering boundaries even further. Shipboard onagers required gyroscopic stabilization systems that kept machines level despite wave motion. Bronze bearing systems allowed the weapons to traverse and elevate while mounted on moving platforms. The siege of Aquileia reveals sophisticated counter-battery techniques. Roman artillery crews used onagers to destroy enemy siege engines, engaging in artillery duels that required precise range calculation and trajectory prediction. These operations demanded mathematical skills that wouldn't be common in European armies for centuries. Mountain warfare applications showed remarkable adaptability. Roman forces in Alpine campaigns used lightweight onager variants that could be disassembled into man-portable loads. These machines provided fire support in terrain where traditional siege engines couldn't operate. Anti-fortification techniques evolved beyond simple wall battery. Roman artillery crews developed specialized tactics for attacking different fortress types, techniques for undermining foundations, creating breaches in specific wall sections, and neutralizing defensive positions without major structural damage. The most innovative application was psychological warfare conducted at strategic levels. Roman diplomatic missions often included onager demonstrations designed to influence political negotiations. Allied cities that witnessed Roman artillery capabilities were much more likely to honor treaty obligations. Roman military intelligence used artillery capabilities as strategic deception tools. False information about onager numbers and capabilities was deliberately leaked to enemy spies, creating inflated threat assessments that influenced enemy strategic planning. Field engineering tactics integrated onagers into comprehensive siege operations. Artillery preparation created conditions for specialized assault techniques, undermining operations, siege tower deployments, and coordinated infantry attacks that exploited psychological as well as physical damage. The evolution toward combined arms tactics represented a conceptual revolution. Roman commanders stopped thinking of artillery as supplementary siege equipment and began treating it as an integral component of military operations at every level. Modern physics reveals just how sophisticated Roman onager engineering really was. These weren't primitive weapons. They were precision instruments that pushed mechanical engineering to theoretical limits that wouldn't be exceeded for over 1,000 years. The torsion system operated on principles that weren't fully understood until the development of materials science. Each rope strand in the torsion bundles stored elastic potential energy according to Hooke's law, the same principle that governs modern springs and shock absorbers. Ballistic performance calculations show that Roman engineers had intuitive understanding of projectile motion that wouldn't be formally described until Newton's principle. Optimal elevation angles, trajectory calculations, and range estimations required mathematical concepts that were centuries ahead of their time. The lever mechanics demonstrated sophisticated understanding of force multiplication and energy transfer. The throwing arm's angular acceleration, followed rotational dynamics principles that wouldn't be formally codified until the development of classical mechanics. Materials engineering reached levels that seem impossible for ancient technology. The bronze alloys used in pivot bearings contain tin percentages optimized for strength and weight resistance. Modern metallurgical analysis shows compositions that wouldn't be improved upon until the development of steel technology. Stress distribution in the wooden frame structure followed engineering principles that anticipated modern structural analysis. Load-bearing calculations, joint design, and material selection showed understanding of mechanical forces that wasn't formally taught until the Renaissance. Quality control procedures incorporated measurement techniques that approached modern precision standards. Roman military specifications for rope tension, component tolerances, and assembly procedures required measuring instruments accurate to fractions of degrees and pounds. The manufacturing processes represented industrial organization that wouldn't be matched in Europe until the 18th century. Standardized components, interchangeable parts, and quality control systems anticipated mass production techniques by over a millennium. But here's what's truly remarkable. Roman engineers achieved this level of sophistication using only hand tools, visual measurement, and empirical testing. No mathematical formulas, no precision instruments, no theoretical framework, just systematic observation and continuous improvement. Modern reconstruction experiments have validated Roman engineering claims that seemed impossible to earlier historians. Computer modeling confirms that properly built onagers could achieve the ranges and accuracy described in ancient military accounts. The physics underlying onager operation remained unsurpassed until the development of gunpowder artillery. Even then, early cannons couldn't match the accuracy and reliability of the best Roman torsion engines. Archaeological discoveries have revolutionized our understanding of Roman artillery technology, revealing engineering sophistication that surpassed historical estimates by enormous margins. The excavations at Hatra in Iraq uncovered the most complete onager remains ever found. Bronze components preserved in desert conditions show manufacturing precision that rivals modern machine work. Bearing surfaces machined to tolerances measured in fractions of millimeters. Gear teeth cut with uniformity that required master craftsmen. Dura Europos excavations revealed an entire Roman artillery workshop complete with specialized tools, component stockpiles, and half-finished weapons. The manufacturing processes showed industrial organization that anticipated modern assembly line techniques. Stone projectiles discovered at siege sites across the Roman world tell stories of tactical sophistication. Different weights and shapes for different tactical applications. Carved markings that indicate standardized military specifications. Impact patterns that reveal coordinated bombardment techniques. The fortress excavations at Masada uncovered Roman siege works that included prepared artillery positions, geometric layouts that maximized field of fire while protecting crews from counterattack, stone platforms designed to absorb recoil from the heaviest weapons. Underwater archaeology has revealed shipboard artillery installations that push our understanding of Roman naval engineering, bronze mounting systems that allowed onagers to operate on moving platforms. Stabilization mechanisms that kept weapons level despite wave motion. Metallurgical analysis of bronze components shows alloy compositions that were perfectly optimized for specific applications. Bearing metals formulated for wear resistance. Structural components balanced for strength and weight. Spring elements designed for maximum energy storage. The timber analysis from preserved onager frames reveals wood selection criteria that show deep understanding of material property. Grain patterns chosen for specific stress applications. Seasoning techniques that maximized strength while minimizing weight. Laboratory testing of reconstructed rope torsion systems has validated ancient performance claims. Modern materials testing shows that properly prepared sinew could store energy densities that rival steel springs. Computer modeling of archaeological remains has confirmed trajectory calculations found in Roman military manuals. Ballistic performance matched theoretical predictions with accuracy that wouldn't be achieved again until the development of modern artillery. The archaeological evidence proves that Roman military engineering represented a technological peak that wasn't surpassed until the Industrial Revolution. These weren't crude ancient weapons. They were precision instruments that pushed mechanical engineering to absolute limits. The fall of the Onager wasn't sudden. It was a gradual obsolescence that reflected broader changes in Roman military doctrine, economics, and strategic priority. By the 5th century, the Western Roman Empire faced challenges that made complex siege artillery increasingly impractical. Barbarian invasions required mobile defense strategies that couldn't accommodate slow, heavy artillery train. Resources that once supported specialized artillery units were diverted to more immediate military needs. The economic factors were decisive. Onager production required master craftsmen, expensive materials, and sophisticated supply chain. As Roman manufacturing capacity declined, maintaining artillery capabilities became prohibitively expensive compared to simpler alternatives. Military doctrine evolved toward rapid deployment and defensive flexibility. The massive fortifications that onagers were designed to attack were increasingly rare. Enemies adopted hit-and-run tactics that made siege warfare less relevant to overall strategic outcomes. But the most important factor was technological. The development of early gunpowder weapons in the 6th and 7th centuries offered advantages that torsion artillery couldn't match. Cannons were simpler to manufacture, easier to maintain, and more adaptable to different tactical situations. However, the transition wasn't immediate or complete. Byzantine forces continued using torsion artillery well into the medieval period. The famous Greek fire projectors used modified onager mechanisms to launch incendiary projectiles against Arab naval attack. Medieval European armies occasionally attempted to reproduce Roman artillery technology, but lacked the manufacturing capabilities and technical knowledge necessary for effective implementation. Most medieval siege engines were crude approximations that couldn't approach Roman performance standards. The knowledge preservation was incomplete, but significant. Islamic scholars translated Roman military engineering texts that preserved theoretical principles if not practical construction details. These translations eventually influenced Renaissance military engineering when interest in classical technology revived. Ironically, the final obsolescence of torsion artillery came not from superior firepower, but from simplified logistics. Gunpowder weapons required less specialized maintenance, could use standardized ammunition, and operated with smaller crew requirements. The last recorded use of onager-type weapons was by Byzantine forces defending Constantinople in 4. Even then, they were supplementary weapons used alongside cannons that had become the primary siege artillery. Modern military historians recognize that the decline of Roman artillery technology represented a temporary technological regression. European warfare didn't regain comparable artillery capability until the 16th century, over 1,000 years after the last onagers fell silent. Modern attempts to recreate Roman onagers have produced remarkable insights into ancient engineering capabilities while revealing just how sophisticated these weapons really were. The most ambitious reconstruction project was undertaken by the Royal Armouries in Britain, working with engineering students from Cambridge University. Their goal: build a fully functional onager using only materials and techniques available to Roman engineers. The results were stunning. After 2 years of research, experimentation, and construction, their onager achieved ranges that exceeded historical accounts. A 100-pound stone projectile traveled over 450 yards with accuracy sufficient to hit a target the size of a fortress gate. But the real revelations came from understanding the construction process. Modern craftsmen, working with power tools and precision instruments, struggled to match the tolerances achieved by Roman engineers using only hand tools and visual measurement. The rope torsion system proved especially challenging. Modern synthetic materials couldn't match the energy storage capacity of properly prepared ancient sinew. The team had to source authentic materials and learn processing techniques that had been forgotten for centuries. German military historians at the University of Munich conducted extensive ballistic testing using computer-controlled measurement systems. Their onager reconstruction generated muzzle velocities that approached modern artillery performance level. The stress analysis revealed engineering principles that weren't formally understood until the 19th century. The wooden frame distributed forces through load paths that anticipated modern structural engineering by over a millennium. French archaeologists, built a scaled-down version for educational demonstrations at the Musée de l'Armée. Even at half-size, their onager produced enough recoil force to shake the entire building when fired. The most comprehensive study was conducted by the Roman Army Research Foundation, which built multiple onagers of different historical periods to study technological evolution. Their research revealed continuous improvement in design sophistication that paralleled broader Roman engineering development. Modern metallurgical analysis of the bronze components showed manufacturing techniques that pushed ancient technology to theoretical limits. Bearing surfaces finished to tolerances that wouldn't be improved upon until the development of precision machinery. Computer modeling validated ancient trajectory calculations with remarkable accuracy. Roman artillery tables proved to be mathematically correct within margins of error that would be acceptable for modern weapons. The psychological impact testing used sound measurement equipment to analyze the acoustic effects of onager operation. The distinctive crack of the release mechanism could be heard over 2 miles away, a psychological factor that ancient accounts consistently emphasized. But perhaps the most important discovery was how much skill was required for effective operation. Modern crews, even with extensive training, couldn't match the loading speeds achieved by experienced Roman artillery specialists. The influence of Roman onager technology extends far beyond ancient warfare, establishing engineering principles and tactical concepts that still influence modern military thinking. Medieval trebuchets were direct descendants of Roman torsion artillery, incorporating lessons learned from centuries of onager development. The mechanical principles, energy storage, force multiplication, and projectile acceleration remained unchanged even as the specific mechanisms evolved. Renaissance artillery development drew heavily on rediscovered Roman engineering tech. When European armies began serious artillery development in the 15th century, they studied Roman siege warfare manuals that had been preserved in monastery libraries and Islamic translations. Modern artillery doctrine still reflects tactical innovations pioneered by Roman onager crews. Concepts like battery formation, coordinated fire control, and systematic target selection trace directly back to Roman military manuals written over 1,500 years ago. The engineering principles underlying onager operation appear throughout modern mechanical systems. Torsion springs in automotive suspensions, energy storage systems in industrial machinery, and force multiplication mechanisms in construction equipment all use concepts mastered by Roman military engineers. Quality control procedures developed for onager production anticipated modern manufacturing standards. Standardized components, interchangeable parts, and systematic testing protocols weren't matched in European manufacturing until the Industrial Revolution. But the most important legacy was conceptual, the idea that military technology could be systematically developed through engineering innovation, rather than incremental improvement of existing weapons. This represented a philosophical revolution that wouldn't be fully realized until the modern era. Contemporary special operations forces study Roman siege warfare for insights into psychological operations and strategic deception. The principles of demonstrating overwhelming capability to influence enemy decision-making remain tactically relevant. Modern project management techniques can trace conceptual origins to Roman military engineering practice. Complex logistics, specialized workforce coordination, and systematic quality control were refined to levels that weren't surpassed until the 20th century. The materials science advances driven by onager development influenced civilian technology across the Roman world. Bronze alloy compositions, wood treatment techniques, and rope manufacturing processes found applications in construction, transportation, and manufacturing. Even today's precision manufacturing draws inspiration from Roman engineering achievement. The fact that ancient craftsmen could achieve such tight tolerances using only hand tools challenges modern assumptions about technological